Welcome to the fastest way to learn data structures and algorithms. Today, we are mastering LeetCode 127, the word ladder challenge. This is a premier graph traversal problem that tests your ability to find the shortest path in a sea of transformations. Let us look at the problem statement. We are given a begin word, an end word, and a dictionary of valid words. Our goal is to find the length of the shortest transformation sequence from the start to the end. There are two strict rules. First, every adjacent pair of words must differ by exactly one letter. Second, every intermediate word must exist in our dictionary. If we reach the end word, we return the total count of words in the path. If not, we return 0. Think of it like a security terminal morph. Imagine you are a secret agent trying to bypass a series of encrypted terminals. You start with the code HIT, and your target is COG. To move from one terminal to the next, you can only change one character at a time. But here is the catch: the new code must be a valid key in the security database. To find the absolute fastest route out, you do not just wander aimlessly. You explore every possible one-letter change level by level, like a wave spreading out, until you hit the target terminal. This systematic search guarantees you find the shortest escape path. To implement this, we use breadth-first search, or BFS. Why BFS? Because in an unweighted graph where every hop costs the same, BFS is the gold standard for finding the shortest path. We first convert our word list into a set for O of 1 lookups. We then initialize a queue with our starting word, and a level counter set to 1. Let us dive into the dry run. Look at the screen. Our begin word is HIT, and our word list is on the right. At level 1, we start with HIT. We try changing every character. If we change I to O, we get HOT. Is HOT in our list? Yes. We add it to the queue and remove it from the set so we do not visit it again. Now at level 2, we process HOT. We try all changes. Changing H to D gives DOT, and changing H to L gives LOT. Both are valid keys. We add them to the queue and move to the next level. At level 3, we take DOT, changing T to G gives DOG, another valid step. From LOT, we can reach LOG. At level 4, we process DOG, changing D to C gives COG. We have hit our target. Since we reach the goal at the next level, our final path length is 5. Now, let us look at the Python implementation. We start by handling the edge case. If the end word is not in our list, it is impossible, so we return 0. We convert the list to a set, and initialize our queue with the begin word. We use a while loop to process the queue level by level. For each word, we iterate through every character position, and try replacing it with every letter from A to Z dash. If the new word matches our target, we return the current level plus 1. If it is in the set, we add it to the queue and burn it from the set. If the queue becomes empty and we have not hit the target, we return 0. For complexity, the time complexity is O of n times m squared. We process each word once, and for each word, we perform m squared work to generate all possible variations. The space complexity is also O of n times m squared, to store our word set in the queue. And that is word ladder, mastered. Save this video for your next interview, and follow Leo Academy for more premium DSA guides.